Hey guys, just a reminder that this is the second part of our discussion on the concept of coding in neuroscience. In the first part, we talked about this report that was written about a conference that took place in the 60s, where a lot of the general concepts about this idea of coding were introduced, and we talked about how they're still relevant for today. In this episode, we're going to get a little bit more into the specifics of coding in neuroscience, and for that, we read a paper called Neural Representation and the Cortical Code by DeCharms and Zader. And then we get into a more philosophical paper called Is Coding a Relevant Metaphor for the Brain by Romain Brett. Enjoy. We can try to talk more specifically about what the neural code could be based on that next article that kind of sums up the more current state of the field. So I guess the idea is if information is being passed around in the brain, we can look at a neuron and its activity, and we should be able to kind of see a reflection of that information passing. And then the question is, what does the brain itself use in that signal? And a big debate kind of historically in the field is this idea of rate coding versus temporal coding or spike timing coding. And so rate coding, as we talked about earlier, is just the idea that you can look at the discharge rate of action potential, so like the number of spikes per unit time, and that information will or that signal will carry information, for example, about a sensory stimulus. So neurons in the visual system will change their firing rate in response to different visual stimuli. And so having that rate information is potentially sufficient to tell you stuff about the visual stimulus that's being presented. Again, I'm doing kind of the lossless encoding style thinking. Like, you should be able to recreate the visual stimulus by the firing rates of visual neurons, which is not an entirely accurate way to phrase that, because ultimately what matters is the information that the organism needs to extract from that input to, choose behavior and that kind of thing. But rate coding is one option. And then temporal coding has always been a bit of a fuzzier concept to me, because, and this paper acknowledges that it's kind of on a continuum with rate coding. It's just the idea that, if rate coding says you should look at spikes per every 200 milliseconds, and that's sufficient, then temporal coding says that you have to look on the timescale of spikes. So a couple milliseconds matters. You have to look at kind of very fine time bins rather than coarse time bins to really get the full information that neuron is encoding.
Well, so there's one subtle distinction they also make, which I kind of like in this one, though, between, like, if you use small time bins, it could still be rate coding. What they try to say is that, like, what temporal coding would be, that there's extra information in the time between spikes or the timing of the spikes that is in addition to the time variations in firing rate that are inherited from the stimulus or input. Right, so like if it's a time varying rate that's inherited from the stimulus, that's still rate coding. There has to be temporal precision in the spikes that actually encodes a non-time varying property of the input. Otherwise, it's just rate coding still.
I can give one concrete example that I know, just so we have a concrete example, which is that in fish that have an electrical sense, specifically in more myrid fish, they have an active electrical sense. They create an electrical signal, very, very brief, like microseconds wide. That electrical signal causes electrosensory input all over the body of the fish, which is picked up by neurons, which are electroreceptors that live near the surface of the fish's skin. And the amplitude of the local electrical field at a given receptor will depend on the shape of the objects in the environment, basically. And so, in theory, if you know the amplitude of the electrical field all over the body of the skin of the fish, you can know something about what's in the environment. And so in that case, there are receptors called mormyromasts, which transduce a non-temporally varying property of the electrical field, namely the electric field amplitude, into a temporal code, which so the information is encoded in the time, the time from the time of the first spike that the receptor fires from the time that the electrical impulse was produced by the fish. So the fish produces an electrical impulse, and then starting from there, if you count to when the spike is fired by the receptor, you can know something about how strong the electrical field produced by the firing of the...
So the timing encodes something that's not timing related about the environment, but amplitude related about the environment.
Exactly.
Yeah.
That's a good example. And so I am much more able to understand the concept of temporal coding when it does involve more than one neuron, because then it makes sense that you have like a clock somewhere, that you're timing in relationship to. And they give an example that's slightly different, but is also, it's a response to a steady stimulus, an auditory stimulus if a tone is played. And there are auditory neurons that will, after an initial transient response to the tone, will have the same firing rate for different tones, but the spike timing synchrony between two neurons will vary depending on the tone. So if you just look at the rate of individual neurons, you can't say much, but if you look at how aligned the spike times are across two different neurons, then you can see information about the tone. But this is open to the question of whether that's actually what the animal uses, because this is something that was observed in animals under anesthesia, and so it's not clear that this is, what's actually happening when these tones are being perceived and further processed.
Mm-hmm. I mean, I think, in theory, I don't know examples of this, but in theory, you could have situations where it's just precise sequences of spikes are required. Like, there's some neuron, and if it goes bop, 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 then there's a fish in the environment or whatever. Do you know what I mean? That's possible.
But I could call that a rate code.
You couldn't.
Well, no. You wouldn't call it a rate code if it's like think about it as the way a password gets used. Like if you knock on a door with a bump, 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 or something like that.
Yeah.
What if the downstream neuron only fired when it received that specific pattern, which was not a temporal inherited pattern. That wasn't from the stimulus. That was the neuron saying, I'm going to unlock the signal to the next neuron or something. I mean, I've now made this a very loose analogy, but the spirit of this point is, right, it has to do something weird and temporal to actually signal something that isn't temporal.
Right.
Yeah, I understand. I guess the idea, though, that you could bin those spikes in some way that you still see that difference, even though you're not looking at the exact spike times, makes it seem like you could possibly describe it as a rate code. But again, this just goes to the fuzziness and the distinction. But yeah, the idea that it's not just a monotonic relationship between rate and identity,
stimulus property.
Then you can say that that's a temporal code. I understand.
Yeah, I mean, obviously, calling that a rate code does sound really stretched, but it's worth wondering why exactly it sounds stretched.
That's the theme of the episode.
But I think what Josh said is really that's actually very useful for knowing when it sounds stretched. It may not cover every case, but the idea that you encode something non-temporal in a temporal sequence.
It's in that case, the encoding of that pattern is either or. You need to downstream have something that's detecting a pattern, which is again, kind of not related to the temporal information, but is related to something about the stimulus is decoded from the sort of timing information, the actual timing information.
That's actually, so it's interesting. I hadn't thought about this before. It's the idea that the more interesting thing is kind of temporal features of spiking activity, being encoding something, non-temporal features of something. Maybe that's a more interesting distinction in certain ways than the usual rate versus spike timing distinction. As in, you could kind of in a way that still feels very forced to me. You could try to call that thing a rate code, but it's just that the neuron has to experience a very particular rate pattern in order to, signal something. Yeah.
Are there examples of that kind of thing? I'm sure that there are, where there's some particular temporal pattern that is distinguishing between different stimuli or different whatever's being encoded, that if you looked at a more coarse binning of it had the same rate, but the rate was just distributed differently within.
I mean, the simplest thing would be bursts, which do kind of roughly this kind of thing. A neuron bursting to a downstream neuron sends information to it that's not, like, the timing there is like, it conveys qualitatively distinct information. It's like, if a burst happens, do this. And if
A burst
there's
being
not
a group of spikes very close
nearby,
together.
yeah, exactly.
Which is different than if they're slightly spread out. But yeah, so the things like bursts or the idea of there being more synchrony in spike times across different neurons, I think are nice things to think about because they actually do consider who's doing the quote-unquote decoding. They consider the properties of a downstream neuron, which says, well, if you get a bunch of inputs at once, that might get you over the threshold that you need for that neuron to spike itself, or the downstream neuron to spike. Whereas if they're distributed more loosely across time, then they won't come all together in like a nice enough way that actually gets you over the threshold. So the fact that neurons, have a threshold of input that they need to reach to spike means that these timing elements can actually matter. And I mean, the rate coding, I think, has obvious implications as well. That just says if you get more input, you're more likely to fire. But the timing elements are also relevant, of course.
So do we want to touch on the philosophy of... So, I mean, throughout we've been hearing lots of examples, and actually these papers give more examples. So like in the first paper, as I mentioned, there's this appendix with lots of examples that they knew in the 60s. And in the more recent paper, there's sort of a qualitative characterization of the different kinds of codes that might be used. Kind of giving evidence, references and evidence of different codes maybe being used without like being too argumentative about which ones exactly are used where. I guess let's touch on maybe the philosophy in this third paper of whether or not this is a good metaphor or something.
Yeah, I think that's a good idea. I think it's worth noting for people that this second paper is very useful if you just want to go through more of a less at the philosophical level, more just like what are a bunch of the different types of codes that people have observed in neural systems or have speculated might be observed in neural systems.
And we mentioned a little bit like rate coding and temporal coding are examples of those kinds of things.
But then there's a bunch of other things about populations and noise and so on. Yeah.
One fact out of the philosophy paper was that if you search neural coding on Google Scholar, there's 15,000 papers from the last 10 years. Which I guess without context, I don't know if that's a lot or not.
Does anyone have a succinct summary of this paper? Like the thesis?
I feel like the overall structure is like, here are some critiques about the coding metaphor, and I guess the end is meant to be a proposal for a better metaphor, I think. Yeah,
I mean, it's pretty clear. Like they asked, the title of the paper is coding a relevant metaphor for the brain? And then the second last sentence of the abstract is, I conclude that the view that spikes are messages is generally not tenable. I mean, that's not directly answering the question, but,
Yeah, but so I did find it actually, I mean, those sort of like obvious statements notwithstanding, I had trouble understanding the argument by which that conclusion was arrived at.
So we can say there are different sections meant to address different things. So the first one is focused largely on the fact that experiments are done within a certain experimental setting impacts thoughts on coding. So the claim is something like the communication channel in these situations involves both the biological system and the experimental system. And so to say that something, a neuron encodes something, what you're really saying is it encodes that thing under these experimental circumstances.
And the way that that's not just a really pedantic point is, that, for example, there can be lots of other, like they talk about a photoreceptor, and they talk about the idea that, you can vary wavelength in an experiment and you can see how the current a current in a cell is varying with the varying wavelength, and you can say, oh, these different cells encode wavelength because they're tuned to the wavelength. But in a real situation, there are going to be lots of other things that are varying in the environment that also affect the firing of the neurons. And so in that situation, just knowing, say, the current or something, whatever it is you're measuring in your experiment, wouldn't be sufficient to tell you about the thing that you're interested in your experiment, like wavelength in this case. So in some sense, it's like a statement that it encodes it under these certain conditions, but the idea that it's encoding wavelength doesn't necessarily translate. It might actually be, I mean, you can still save the coding metaphor by hypothesizing that there is some complete description of the system as an encoding system. So that would be a way to kind of challenge this as a challenge, if that makes sense.
I agree.
I found this to not be like a super great philosophical point, because it does just feel like a technical scientific point, and it is something that people are aware of. And so basically when you normally think about a cell encoding something, you create like a one-dimensional tuning curve. Like I vary this one parameter and the cell's response varies. But people also construct two-dimensional and higher dimensional tuning curves that say when I vary these things together, or each of these different input parameters separately, the cell's response varies. So it's not so difficult to expand the coding metaphor to encompass the fact that cells respond to multiple combinations of parameters.
And people are even pushing experiments into like more naturalistic settings where the implication would be that you're not necessarily even recording a tuning curve per se, but you're trying to learn about the information that the activity of neurons in response to arbitrarily complex natural kinds of stimuli.
A kind of philosophical point, though, that is related to stuff we were talking about earlier, is that they talk about the experimental context. They also talk about the context in general, like codes being context dependent in general. So, like, for example, the context could be, if it's an animal, right? The context would be like, what was the animal just thinking about? If animals think, I mean, humans think, right? Or does this animal, is it hungry? Or like, all kinds of like a huge, or like the emotional state. You can come up with like a massive arrays of different things that you could maybe call context. And you could sort of argue that it's about this continuity kind of thing we were talking about earlier. Like at some point, I think it's okay. I mean, I kind of agree that at some point it kind of starts feeling stretched to keep talking about coding, and they're trying to push us towards talking about like neural sensitivity or something. I'm not sure why we can get into why their alternative metaphor at the end, but like the point just being that if you have to take into account like a massive array of other things in order to then really make the kind of most direct sense of the idea that it's encoding certain types of information, then maybe you should drop the coding metaphor. But
yeah.
I mean, but then the whole later part of the paper talks more about thinking of neural signals as actions rather than as messages. And I feel like, though this person's presenting this as an alternative, this was, as we discussed, sort of anticipated in the language and, conceptual exploration done in the older paper, right? I mean, they make it clear that, interpretation of encoded signals might be the production of actions at the output, whatever the output is, even like the motor periphery, the ability to interact with the environment. So, like, I think when the coding formalism is taken still literally, but just slightly more generally, it allows for actions. I mean, as we've discussed kind of thoroughly already, it allows for actions to be part of the code space, right? Actions can be an output code. And so the distinction between a message and an action isn't entirely clear to me, like in a formal sense. Actions are codes which affect the environment in some sense, right? I mean, I think information theory people or information theoretic people who deal with this kind of stuff would be okay with that usage.
I just want to jump back to the idea that context can change the rates or the responses of cells, and how that might complicate the coding metaphor. Because I think I mean, maybe I'm so well trained in neuroscience that I can do this for anything, but I can make that fit into a coding metaphor framework because it's just saying, I mean, it's complicating things because in those situations, a lot of times how you would think of it is to say that the decoder has changed maybe. So, if you're hungry, the fact that there's a stimulus that looks like food is going to have a different impact on your action selection than if you're not hungry. But you can still say that this cell is still encoding the information, but then the decoder is different in a different context. It's a potential way to frame that.
Or even to make that a little bit more unified with what I'm trying to say, like the re-encoding of the information about the stimulus is biased based on your ongoing desires, right? So like if you're hungry or not hungry, the way you re-encode towards actions. And I mean, I'm like, obviously this is just still trying to force this paradigm, but again, there might be some utility.
Yeah, I agree. No, it's your re-encoding is different. But there is something...
It's context-dependent re-encoding.
So the notion that different environments lead to different encodings, or the fact that, cells actually have high-dimensional tuning curves, quote-unquote, I think that should have an impact on the way people think, not necessarily for the reasons that this article is saying, but it does seem like when people find something that they can plot a tuning curve for, they then make assumptions about the function of those neurons. And that's a leap that I think is too far. Because you could have a cell that is responding to, its firing rate does vary with a change in a stimulus. But to say that then that is the role of that neuron to encode that parameter, I think is probably faulty, because it could, encode a great many other things as well. And so I think our desire to have interpretable encoding frameworks is perhaps problematic, because it forces things to be simple and to map onto like units that we already instinctively feel. But the coding metaphor itself could theoretically be expanded beyond that. But I think a lot of the benefits that have come from the coding metaphor is the idea that things are encoded in ways that we understand.
Yeah, I mean that's a good point, and I want to avoid being too philosophical all the time, because there's lots of really simple things that are actually a little bit striking if you think about them. Like related to what you just said, Grace, there's a question of, and this was actually referenced in the 1968 paper, of like they talked near the very beginning about the relevant properties of the world that are encoded or something, or that affect neural activity, and this is one aspect of what you were talking about. The other aspect is that the codes can be like really, really complicated, but it's just like that which is even meant to be encoded is unclear. So like I was just thinking of an example would be like, there can be non-intuitive things in both directions. So for example, like it turns out that it might be very important to animals to encode the exact, at a very high level of resolution, the difference in timing between when a sound reaches one ear or the other, because that can give you information about where an object is, right, based on the sound that it emits. So that's like, you have to encode something, a very tight measure of the difference in the time it takes for a sound to hit one ear versus the other, that you might not realize, like it's not intuitive that that's an important thing to encode until you understand that it can allow you to decode position, right? So there are things that you might want to encode that are kind of not intuitive that you might want to encode. And on the other hand, there's also like, there are things that are intuitive to us, that intuitively seem important about the world to always encode, because we always encode them, we think, that might just be totally irrelevant to certain animals. So like, for example, a really striking example of this, I think, is that like lots of animals see color very differently. Like different animals have very different photoreceptors, for example. So they presumably just perceive color differently. Presumably, and we know like we can only perceive certain colors, which means that we are kind of, as organisms, constantly ignoring lots of color information in the world. So we don't, as organisms, somehow find it relevant on an evolutionary timescale to encode that information. I mean, yeah, so that's slightly stepping back, but just to give some concrete examples of this, of how really it's not obvious what it means, what the relevant things to encode are.
So, I mean, I will return to this other thread, though, which is, it's unclear to me how the paper presents a totally unified argument. It tries to make some technical points about whether encoding is like feasible or it's accurate to think of what happens in experiments as representative of encoding in natural situations. And then it tries to make a second point that I don't see as totally tightly related about whether whether signals should be thought of as messages or actions. And it's not clear to me that there's a very deep distinction between the two. Like there is clearly colloquially, we mean different things when we say, is that signal a message or an action? But I'm not sure that there's at a mathematical level much of a difference. So I take the criticisms of this paper relatively lightly. I'm not convinced that it makes some substantial claim that I feel lands in an interesting way.
Yeah, but at the same time, this relates again to the thing we were talking about at the very start about this tension between metaphors as usefully constraining. Let's say there was some way that you could speak about things that was about action, and there was some way you could speak of them that was about information, and then you could come up with a mathematical formalism where it's these are just dual ways of speaking about the same formalism. You could say then that the critique is irrelevant. But,
that's kind of my feeling, yeah.
Right, but then at the same time, sorry.
I was just saying, the point of something like math is to abstract away things. So sure, it's when you put things in a more abstract space, more things are going to come out as being the same.
Right, and so exactly, and so the thing that's the point. I mean, the thing about metaphors is that they're not the same as formal systems. Part of why the metaphor is useful is because it has colloquial connotations which structure our thinking. And constrain us so that it makes it easier to kind of hypothesize, I think.
I guess if I'm being generous to people working in the contemporary field, I would say it turns out maybe that a metaphor that was used about communication channels and which math was provided for actually holds in a slightly more general setting. And in the math that was designed to correspond to the metaphor of communication channels, the distinction between messages and actions is irrelevant. And so it's not clear that a philosophical criticism about whether the signals are messages or actions necessarily matters because people were using the math. Again, they built the math to correspond to a metaphor of communication channels, but the math is what they're really using in the background. When people are doing theorizing and quantitative stuff related to what's going on in the brain, they're using this math.
But you can imagine, yeah. We've already talked about an example where the metaphor and the style of thinking matters, because if you have truly an encoding mindset, then you will say, if I can read out this information from this area, then that's something that's relevant. Whereas if you have the more action mindset, what does this do to the next area of the brain or to the behavior, then that just being able to read it out isn't sufficient, and understanding the process is more important.
No, but I think that this is covered. I don't want to be a weird pedantic person saying that the original document covered this and therefore it's not relevant. But it is the case that when they proposed the metaphor, they said, there's a special category for information that is encoded but not used, and it's not really part of the code.
Yeah, but we all agreed that the messages of that original document have been lost through time.
I agree, but so I don't think it's a legitimate statement wholly to say that if something is decodable, then it's part of the code. I think that's an elision that people have tolerated right now, but it's not clear that that's deeply required for the coding framework.
Yeah, but there are styles of thinking that will be encouraged by certain metaphors and discouraged by others. And that's all that it takes. When you have a bunch of people interacting with each other and they're all slightly geared towards a certain style of understanding, it can have large effects.
I think that's right. I think that's very worth remembering. I think it can be part of. It's not something that you have to try to eliminate. I think it's just. I suspect that's a useful thing to bear in mind when thinking about something about the sociology of how science works. Or something, and it may be that then a useful thing to do is to kind of acknowledge, right, like I did at the start. Also, these people may have the people who wrote the 68 paper, I think, actually did kind of predict, or they already we're addressing. Some of the things that are being brought up here, but like maybe now, given there's been like a long period of thinking in a certain way, it's useful to start wondering about these other ways of thinking. I'm vaguely, I'm not like strikingly convinced by this paper, but the idea that I think the action alternative isn't very. They don't propose a lot of detail. The coding and informational metaphor comes with a lot of meat because there are kind of whole other fields built around these notions, and so you can borrow a lot of concepts. I think you could use the action metaphor. If you'd have to do the work though. You'd have to like find other fields where notions of action are central, and certain types of like dynamical system stuff comes to mind, mechanics and things like this, and maybe also things in like AI kind of like or like the study of behavior, like kind of something about like intentionality and strategy, those kinds of things. I don't know how useful those would be as metaphors, but
yeah. But I guess part of what I was sort of alluding to is like even when you talk about decision-making processes in a formal sense where actions are part of the game, you still can use these sort of information theoretic quantities where you talk about the information of the action space or the relationship between the information of the incoming signal and the outgoing action. The formalism kind of just holds in those settings to some extent. I mean, it's still meaningful to think about like information and the distinction between coding where the output is a message and coding where the output is an action. They're both variables, and you can treat them kind of the same from a mathematical standpoint to some extent.
I think the bringing up AI is an interesting idea for this because a lot of times these are systems that are trained end to end, meaning that all of the ways that the neurons connect to each other are trained together at the same time. So there can be kind of strange dependencies. It's not like you're saying, I'm going to train up a system that does this really simple task, and then I'm going to feed its output into this other system that was trained to do a simple task. And so they're hard to understand if you isolate any unit of them, because it really is the case that it works as this full big system. And I think that's relevant here because, you can still talk about encoding. You can still make tuning curves for neurons in artificial neural networks. But it's clear that it's hard to understand them. And it makes it seem like we shouldn't expect to understand encoding at any given area of the brain if the system was really built in a more end-to-end way. Oh, there was also this paper used this Paramecium example, where this is a single-celled organism that has sensors for certain chemicals that it uses as food, and if its sensors say that they're not receiving a lot of this chemical, so the membrane gets depolarized and there's a spike, and that causes the paramecium to just change direction, and it's just like this very small system. That it seems like, in that system, we wouldn't necessarily feel the need to talk about encoding the cell that, the membrane potential, changing technically is encoding stuff about the level of chemical in the environment. But because we just understand the system so fully, it doesn't feel necessary to speak of it that way. And to think of it as like an action chain is totally reasonable. And I think that is relevant. As I said before, I think the coding stuff helps us deal with the fact that the system is complicated and we want to be able to break it down into units. But in reality, it is just this long chain of, neural inputs to muscle outputs.
Yeah, it does seem like there's some kind of central tension there between just like a domino view of the brain, or like a current or something, like a liquid or something view, versus like a discrete units talking to each other and then finally doing something like that. In the paper they also talk about the idea of extrinsic versus intrinsic information, and the idea so like There's a sentence I'll just read it. I'd say, in the coding metaphor, neural activity is information about the world in the sense that it is possible to reconstruct the external world from neural activity, just as it is possible to map a Morse message back to the original message. The problem is a Morse message translated from German is not informative unless one understands German, and it is even less informative if all that the receiver ever gets to observe is Morse messages.
Yeah, I feel like this so they call this the Tower of Babel, like criticism basically, which they made up, they're proposing, which is just that each neuron has its own language. I don't think that that's fair because it's clear that the neurons learn to communicate with one another. The whole system is learned.
I also, exactly, and another thing that's really related to that, just I'll add it in so you can synthesize, which is that neurons don't have to be like people, right? They can be able to hear and understand one language and speak in another language. Do you know what I mean?
Yeah, it's sort of obvious. Like in a computational process, obviously you're going to be listening to your inputs and you're going to be speaking to your targets. And as you said, they're going to, I think that's actually a really clever way of criticizing that point, which is because it's asymmetric, you learn how to speak to a specific downstream target or to a set of downstream targets, but you learn how to listen to the inputs. And so if the inputs are providing you useful information in the context of a system that's learned, you're going to learn how to extract the useful information from those inputs. I mean, in some way, this whole criticism, this Tower of Babel criticism, feels like totally wrong. Like not even.
Yeah, I mean, so they were trying to claim that, like neurons. How is it possible that neurons can understand each other because they're all like individual entities?
It's like they're learned.
Yeah,
so,
no, so
like
I agree
they
with
learn
that.
to communicate.
But
with
in a
one
way,
another.
that description doesn't feel super encodey, decodey to me. You're saying like, well, they learn to all act as this unit that just can take in something and pass out something else. And I don't know if that's. I mean, I could see that that's still a valid, slightly alternative framework to the encoding one.
I think we're coming up against the ways in which the thing kind of breaks on our intuitive notions of the word encoding, but we see, if you look very closely, that you can just change those notions a little bit, and they're still like our notions, but not completely like them. Kind of, I don't know how you decide. So they're trying to make a very firm thing, which is like the metaphor doesn't work, but it kind of seems more like the metaphor kind of works, but not perfectly.
It's only if you're like overly strict about what you mean by the metaphor in a way that the people who proposed the metaphor never were. I feel so. I'm still unconvinced by like kind of any of the major.
Well, there was another point brought up that we shouldn't, and I kind of talked about this before, but we shouldn't expect quote-unquote efficient coding out of the nervous system because it wasn't designed to encode the things that we're checking how well it encodes, because it was designed to, transform and pass along things for the purposes of actions. So, I mean, I think that is true. That's not necessarily, again, not a complete criticism of the coding metaphor, but just saying what should we expect to see when we look at encodings. We shouldn't expect optimal encoding necessarily.
Yeah, I think a number of their specific points were useful and like worth pointing out, and relatively simple when pointed out, but like worth thinking through and pointing out carefully. Caveats, and especially when it's about the simple cases in which we usually think of these things. I think it does feel like a fairly major overreach to go from that to this very strong claim.
But we do agree the Tower of Babel point is just like...
Yeah, the idea that neurons can't speak to each other is not something that landed with me.
I mean, the key thing there is that they claim that this idea that kind of neurons are all like reading, different neurons are reading different kinds of input information and kind of sending information. They're all sending information in different ways. That if you think about it that way, and then you also try to think about neurons as passing messages, it seems like it's a Tower of Babel or something. I mean, I think the thing I said before kind of gets at the point, which is that, like, yeah, if you make the metaphor strict in a certain way, it doesn't work here. Like, it's not a language. You can't think of it as a language in the exact same way as we think of human language, because in human languages, people are always. It's very specific. Like, we understand a language and we speak a language, and they're usually the same thing. And it's certainly the case that it's almost always the case that if you can speak a language, you can also understand it, and if you can understand language, you can also speak it. Although I'm sure there might be.
No, but like an example, like a cool example would be, I mean, people, we both know people who speak who can understand languages like that their parents speak.
But can't really speak them.
But they don't speak them. Yeah. But another point would be just like, think about a baby and a parent. A baby cries, and it's not a symmetric kind of communication. A baby cries and the parent has to understand what the baby means when it cries, but it doesn't respond by crying.
Yeah. Well, right? Some parents do.
They respond.
That's a great example. Because parents understand crying, but they're not actually able to communicate by crying natively. You know what I mean? Like you would be really hard to figure out. If I wanted to try to get you to feed me, I would have to try.
They learn to read their baby's cries, but and that's learned, right? They learn to read their baby's cries, but then they act in ways that are productive and respond to those
not
things,
by crying.
Right?
Yeah.
It's the same. Like dogs understand humans, but they don't express themselves in the same way.
Right. So that's just this thing is only a good criticism if you have an extremely limited version of what messaging means, seemingly premised on like details of most adult human language communication, but not even all.
Which is not what communication channel math really corresponds to,
right,
for the most part.
But Josh, I have a particular thing that maybe you'll find relevant, because we had talked about this before. So there was a very well-known computational neuroscience finding that sparsity is important. If you have a neural code that is sparse, meaning like not a lot of the neurons are active, that can help explain why in the visual system you have cells that respond to oriented lines. Based on like the statistics of natural scenes and the notion that you want to build a code that is sparse, you can explain this finding that neurons respond to different orientations. And so that was kind of put forth. I mean, that's totally within the coding metaphor. It's making claims about what kind of code you would want. And it was put forth to explain this thing that was found. But then now we know that if you train a deep neural network to do visual object recognition, so this is one of these big end-to-end things that you just train as a big giant unit, and you're not enforcing any kind of sparsity, you also get cells that respond to orientations. And so I feel like this is a concrete example of where like the coding metaphor is coming up against a larger kind of functional analysis of a system. Mm-hmm. And, maybe, I don't know how to interpret those things, if they're findings that are at odds with each other, like the sparse coding idea isn't relevant, or they're two different ways of looking at something in some way. I don't know, but at least it points to the idea that thinking of things as encoding led us down one path, and not thinking so strongly about stuff as encoding, but more as just a giant process that is meant to complete a goal, led us down a different path, and now they're both explaining actual data.
Yeah, no, I think that's an interesting point about whether if two alternative perspectives can explain the same data, what does that say about the relationship to each other? I think in some ways, my only answer is like sort of the simple one, which is like, if the data is able to be explained by multiple theories, then you need more data to differentiate between those theories. Right? If training an image classifier end to end can explain orientation-selective neurons early in the visual stream, and sparse coding can explain orientation-selective neurons in the visual stream, maybe we'll find there's some like hidden relationship between like deep nets learn something sparse, and maybe there's already findings on that we just are unaware of. But alternatively, we just, it turns out that a lot of things could explain that finding, and you'll need more data to differentiate between them. Or in some ways, both of them are true. But I mean, this could be coincidental. I mean, in some sense, both of them potentially explain this finding. So we definitely need more data to arbitrate between them. But like, it's also possible that they're somehow compatible.
But there is this other component that you referenced earlier, Grace, which is that there's also the question of like, and this is obviously something you can't, it's very hard to know, but there's also the question of like, how will people following those two different paths, given that we don't have the data to currently differentiate between them, and given that it's hard for people to keep all the possibilities in mind usually, how will that bias and move over
Their
the next like
behavior
limit,
experiments, yeah.
non-infinite amount of time, kind of, right? Like, which may have effects on the field, blah,
Yeah.
blah, blah. So, which is kind of the question they try to get at the end. Like, they acknowledge, like, the metaphors are not true or false. They're kind of saying, like, we're trying to talk about which ones we think are most useful now. I think we're all on the same page in that regard.
Yeah, I mean, you definitely want to pursue the metaphors that seem like they're fruitful, right? And by fruitful, I just mean give you lots of information that helps you start differentiating between alternative hypotheses and stuff like this.
Should we wrap up? Any final words?
I think so.
Just one last thing, just from because it's from their conclusion. I think this is the one kind of just point of just like emphasis that I did kind of like from their paper, which is like they say presumably an organism is not. I think you already mentioned this, but presumably an organism is not so much interested in reconstructing the sensory signals as in obtaining information about the environment, and capturing signals is only a means to that end. So yeah, something about like an emphasis on that I think is probably useful given the way we tend to think about neuroscience now, because there is a very heavy kind of not actually, it's changing a lot now I think, but there was for a long time, especially in like vision, a pretty strong emphasis on the kind of representational thing, and there's a tendency already for people.
A slight pushback on that, which is not to undermine the point. I mean, I agree with the point, but I think it's a fair approximation for humans, like, or organisms in general with like a rich visual perception, that it's plausible that much of what the early visual system is doing is totally preserving a lot of, I mean, not like at some level of resolution, much of the visual system is trying to preserve a lot of the information and represent it in a way that's useful. Yeah. I mean, keeping in mind that you don't need all of the information, you only need the information that, first of all, evolution has like enabled you to gather, right? The right wavelengths and stuff like this. But also, you're going to filter out some stuff. You're not going to see white noise, right? But you won't be able to differentiate between two frames of white noise on a television screen, right? Because you don't care. And so like it's clear that we don't pick out everything, but at some level of abstraction, a lot of what we're trying to do is clearly to represent a lot of what's going on.
Sensory systems.
Yeah.
Which is where a lot of this has developed as
a
metaphor and as actual work.
Yes. So. Again, which is not to undermine. I mean, it's obviously worth keeping in mind. It now seems obvious, and that's part of what the point of this is. That like keep in mind that you only need the information that you're going to need for taking actions on. But like humans are complex organisms that have to do lots of different things, and you don't know what you're going to have to do always when you perceive things. So sometimes it's clear that for humans, given the capacity, it would be useful to like also see things that you don't immediately need because you're going to want to commit them to memory for potential later use. Humans, so like you do need to pick up a lot of information from the visual world. And if you can, you might as well remember a lot of stuff, even stuff that you're not immediately using, just because it might be useful. It seems very plausible
that humans are actually weird amongst animals in this way. Like maybe we're amongst the animals who retain the most. We're probably the animals for whom like it's least clear immediately what information is relevant or something.
I mean, maybe I imagine a lot of mammals are to some extent like this, but certainly like.
Yeah, I do think the metaphor has brought a lot of progress to the field, but I think it is possible that the field has matured to a point where moving away from it is plausible now, which is a big part of whether you can move away from it or not. But I think it's plausible and potentially beneficial to be exploring slightly different ways of framing the work.
And to Josh's point, I mean, like you're kind of saying that like. It can be just that this metaphor was very good for a lot of work that has been done, and that the real criticism is when people start, because that work was so influential, using the same ideas and concepts and metaphors in other areas where it might not be as applicable, then maybe there it's a good idea to start rethinking it. I mean, this has definitely clearly been happening over the last couple of decades, or certainly over the last 10 years. I think there's like a big emphasis now on more like action and that end of things, and how things might be, how neural signals might mean very different things in more explicitly action-related parts of the brain and stuff like that. But
I still have a nagging suspicion on some level that as the verbiage related to the metaphors change, Like right now, there are people who are engaging with this sort of communication channel metaphor without knowing information theory. And if you're talking about the words, like, is it useful to think about neurons as like communicating information, sending messages? I buy that for like sort of guiding your qualitative intuitions, maybe that has limits as to where that metaphor is useful. I do, on a sort of deeper level, question whether the math that people are using that's like is going to change in meaningful ways, or whether like people might overstate how much the math needs to change because they're the people who are going to try to change the math.
Yes, the math may very well be similar, but as we said before, like how you conceptualize things can still matter for the trajectory of science.
Yeah, I agree.
All right. Till next time.
That was an unenthusiastic till next time.
I like diversifying. Hey, if you're still listening to this, you must really like us. So how about you go to iTunes or Stitcher and rate the podcast, give us some feedback. You can also go to our website, unsupervisedthinkingpodcast.blogspot.com. You can comment on different episodes, or you could give us ideas for new topics you want to hear about. We would love to hear from you. Thanks.